class, today we're talking about properties of rational functions. Now, in order to successfully go through this section, you must be pretty good about properties of polynomial functions already. Now, if you're not, you need to go back and review that first before you can move on to this, because that's really important before you can get to the rational functions. That's because as we study rational functions, we'll find out that they're functions in the form p of x over q of x, where both p of x and q of x are polynomial functions, and q of x is not the zero polynomial. The domain for this rational function is the set of all real numbers, except for those which the denominator q of x is equal to 0. Let's go into that a little bit more. To find the domain of a rational function, we must first remind ourselves of the rule in words. That is, you have to remember the denominator cannot be equal to 0. So that's going to be my first question. What is the rule in words? I expect you to write either the denominator cannot be equal to 0 in words, or the denominator is not equal to 0. So then I'll ask you to write a specific rule for the given rational function. So the denominator of this rational function is x plus 2. I'm going to write x plus 2 is not equal to 0. Next, we're going to solve this. So I'm going to say x is not equal to negative 2. And then there's my domain. That is, the domain is all the numbers except for x is equal to negative 2. Let's find the domain of the second rational function that's given. First, let's write the rule in words. Notice how I shortened the word denominator, D-E-N-O-M. Please, if you shorten the word, you have to spell it this way and not spell a different word. I see a lot of people sometimes write the word domain. You don't want to do that. So denominator is not equal to 0. We'll replace the word denominator with the actual denominator of this rational function, and then we're going to factor to solve. So after you factor, then you can set each factor not equal to 0, and there we go. We have those two terms, 5 and negative 3, that x cannot be. So let's write that in set notation. Anytime I have more than one number and they're distinct numbers, I always want to put them in set notation. There's my answer. My domain is x, where x is all the real numbers except 5 and negative 3. Let's do question number 1 from the notes. It asks us to find the domain of the rational function f of x is x over x to the 4th minus 1. So once again, following the steps we put aside, we're going to write the rule, and there's the rule in words, and then we're going to replace the denominator with the actual denominator from this question, which is x to the 4th minus 1, and then we're just going to solve by factoring. And so there we have it factored out and solved. Even though it's x to the 4th, I actually only have two numbers that cannot be in the denominator because the x squared plus 1 was prime. So my domain is going to be all the values of x that are in the real numbers except for negative 1 and 1. And that is the domain for this function. Let's do question number 1 from the notes. It asks us to find the domain of the rational function f of x is x over x to the 4th minus 1. So once again, following the steps we put aside, we're going to write the rule, and there's the rule in words, and then we're going to replace the denominator with the actual denominator from this question, which is x to the 4th minus 1, and then we're just going to solve by factoring. And so there we have it factored out and solved. Even though it's x to the 4th, I actually only have two numbers that cannot be in the denominator because the x squared plus 1 was prime. So my domain is going to be all the real numbers except for negative 1 and 1. And that is the domain for this function. Well, what happens at the values of x which make the denominator 0? Well, there's going to be a hole in the domain at these values of x. And you can't divide by 0, but as your values get closer and closer to that x, the denominator will get closer and closer to 0, so it's like we're dividing by 0, And so the y value of the function will approach infinity. Let's see what that looks like. In this function, I have f of x is x over x minus c. The variable in the function is x, but the whole is going to be at c. And so let's draw what that graph would look like. So c would be a value on the x-axis, and because I have a hole there, I'm going to draw a dashed line. And this dashed line is going to show you that I can't have the function cross over here because I don't have c in my domain. So c gets thrown out of my domain. And then the graph is going to look like a dashed line at c. Now most typically we'd see the behavior of a graph looking somewhat like this, where it would be going up on one side and be going down on the other side. Notice that as we approach c, the value goes to either positive infinity or negative infinity. So we're going to learn how to write that notation. We're going to use an arrow to show that the x value is approaching c. And we say as x approaches c, then the y value is going to approach positive infinity or negative infinity. Which one? Well, that depends. Which direction are we approaching c from? Well, if we say that we're approaching c from the positive side, meaning from the right side, then we know that it's going to up to positive infinity. So we're going to say as we approach c from the positive side, then we're going to approach positive infinity on the y value. However, if we're going to approach c from the negative side, and you're going to put the negative on the other side of c, not in front of it, then we're going to approach negative infinity. Then we would say it like negative infinity. But this could change, so it depends on however the graph looks. I want to reiterate, when I say c plus, that means I'm coming at c from the right hand side. When I say c minus, that means I'm coming at the c from the left hand side. It depends on which side of the graph you're coming from. Looking at this next function, we see f of x is equal to 1 over x plus 3 squared. So we have the domain where x is not equal to negative 3. Let's graph that. At x equals negative 3, I put a dashed line vertically, so I know not to cross that value when I make my graph. And this graph actually looks more like this. Both of the sides point up to positive infinity. Let's write our sentences as x approaches negative 3. In this instance, as x approaches negative 3, it doesn't matter which side x approaches negative 3 from, because either way, y approaches positive infinity. So it doesn't matter if we're coming this direction, we're still going to be going up. Or if we're coming from this direction, we're going to be going up. In this case, we don't need to specify which side we're coming to the negative 3 from, because both times it's going to go up to positive infinity. So looking at g of x, we first want to think about the domain. And the domain is all real numbers except for x is equal to negative 4. Looking at the graph, we would want to draw that vertical line at negative 4. And you can see that on one side it goes to positive infinity, and on one side it goes to negative infinity. So we're going to have to write two different sentences this way. I wrote most of it, but I'm going to leave some of it for us to fill in. As x approaches negative 4 from the positive side, it's positive on the right hand side. As we approach it, then we're going to be going down to negative infinity. So I'm going to say y goes to negative infinity. But as I approach negative 4 from the negative side, because this is the left side, then my y values will approach positive infinity. So notice the placement, and it comes after the value of negative 4, because the negative 4 tells me where it happens, but the plus and the minus just tells me which side am I coming from. That vertical line at x equals negative 4 would be called an asymptote. So my hole in my domain is at negative 4, so my asymptote happens at negative 4. The equation of the line would be x equals negative 4, while my domain says x is not equal to negative 4. So those are a little bit opposite of each other. The behavior of the graph at the asymptotes goes to infinity or negative infinity. And when I have multiplicity 1, then my asymptote has behavior where on one side of the graph is positive and one side of the graph is negative. Notice that it goes up to positive infinity and down to negative infinity here. That's because the factor x plus 4 in the denominator was to the power 1, so it had a multiplicity of 1. So my asymptote and the behavior at the asymptote behaves the same way as the zeros of multiplicity 1, where on one side of the graph it's above the x-axis and the other side of the graph is below the x-axis. Let's compare that with this new function h of x. The denominator is x minus 1 squared, so that means that since my denominator cannot be equal to 0, then x minus 1 squared cannot be equal to 0, so x cannot be equal to 1. So my domain is all real numbers except where x is equal to 1. Let's graph that. Based off the hole in my domain at 1, I'm going to put an asymptote at 1. So there's my asymptote at x equals 1. And then I'm going to make sure that I know that I'm going to go in the same direction on either side of this, because this was multiplicity 2, which means that it's even, and so the behavior is going to go to the same direction. We would know that the y-intercept is negative 3 by plugging in x equals 0. And we know that the behavior on either side of the asymptote should go the same direction, so they're both going to go down to negative infinity. That's because the multiplicity is even for this asymptote. And so there we go. Let's go ahead and write the behavior of the graph. As x approaches 1 from both sides, then y will approach negative infinity. And we don't have to make two statements, because the behavior of the graph goes to negative infinity no matter which direction we're coming from. To recap, the vertical asymptotes happen at the holes in the domain. So notice the domain will say x is not equal to negative 3, while the asymptote happens at x equals negative 3. And you're going to draw that vertical line at x equals negative 3, and then the behavior of the graph at the asymptote depends on the multiplicity. So if it's even multiplicity, they're both going to go in the same direction, like maybe both of them going to positive infinity. Now looking at the other one, we see that this is, the domain is x is not equal to negative 1, so therefore the asymptote is at x equals negative 1. The multiplicity is 3, so then we know the behavior one side goes up to positive infinity, the other side goes down to negative infinity. Now let's practice finding the domain and the vertical asymptotes of this rational function. I wrote it in factored form just to make it a little bit easier to use. But when we're looking at the domain of this rational function, the only thing we care about is the denominator. So I'm going to set that denominator not equal to 0. And so I'm going to get the domain that x is all real numbers except for negative 4, negative 2, and 1. However, when I look at the factors of the numerator and the factors of the denominator, it should be evident that I could reduce this fraction. And I could write it as little r of x is x plus 5 over x plus 2 times x minus 1. Now notice I changed the name of the function. It used to be called capital R of x, and I'm calling it little r of x. And in all areas it should look the same as this graph, except for I just reduced it. However, this one has a different domain, so we can't call it the same function. But the reason I'm doing this is because I want to find out where the asymptotes are and where the hole is. The asymptotes are at the zeros of the reduced function. So my vertical asymptotes are going to be at x equals negative 2 and at x equals 1. Even though there was 3 factors in the denominator for the original function, there's only 2 vertical asymptotes. What happens to that third hole in our domain? Right? We have 3 values and only 2 of them became asymptotes. Well, the negative 4 is going to be a hole in our graph. To find the specific location of that hole, we take that value, -4, that got reduced, and we plug it into the reduced function. So I'm going to plug -4 into little r. When I plug in -4 into r, I get 1 over 10. And so I have a hole in my graph at -4, 1/10. And so you'll see that later when we come into graphing. Specifically right now, I want to practice though that we're finding the domain. Our domain has 3 holes in it. 2 of those holes in the domain become vertical asymptotes with the equation x equals, and then the third one became a hole in the graph. Now you can have many vertical asymptotes, but you can only have one horizontal asymptote. In the case of this function f of x, what we have are 3 holes in our domain based off of the 3 factors in our denominator. Our domain is all real numbers except for -4, -1, and 2. Our asymptotes are going to be at -4, -1, and 2. And each of our asymptotes has a multiplicity of 1 because those are all to the power of 1. So you notice that each of the asymptotes, one side goes to positive infinity, the other side goes to negative infinity. And that's every single time. Let's figure out how we find our horizontal asymptotes. In this case, our horizontal asymptote is at y equals 0. Our horizontal asymptote is at y equals 0. Notice that we cross the y equals 0 line several times, but it's only the behavior at the end. So it's only what happens as I'm going to positive infinity and what happens as I'm going to negative infinity, what happens to the graph. You can see that the y value gets closer and closer to 0. So we don't care if we cross the horizontal asymptote, we just care what happens at the end behavior. To find the horizontal or the oblique asymptote, the first thing that we have to do is figure out the degree of the numerator and figure out the degree of the denominator. We're going to call the degree of the numerator n and the degree of the denominator m, and we're going to compare them. And based on their comparison, there's different rules for the equation of the horizontal asymptote. Now keep in mind that the vertical asymptote's equation were always x equals because they were vertical lines. But when we're talking about horizontal asymptotes, they will all be y equals, and that has to be part of the equation. You always have to say your equation as y equals, or else you're just giving a value, you're not giving a line. Our first case is when the degree of the numerator is less than the degree of the denominator. In our example, f of x, the numerator has a degree 1, the denominator has a degree 4. And so this is where the degree in the numerator is less than the degree of the denominator. Therefore, it has a horizontal asymptote, and the equation is y is equal to 0. So the horizontal asymptote will be y is equal to 0. In other words, it will be at the x-axis. And this is going to happen every time the degree in the numerator is less than the degree in the denominator. Now, if the degree of the numerator and denominator match, like in this example g of x, then we just take their leading coefficients. In this case, I would take the 4 over the 6. And you always want to make sure that you reduce the fraction if necessary. Since we can reduce 4 over 6 to be 2/3, my horizontal asymptote will be at y is equal to 2/3. For h of x, because the numerator has a degree that is exactly 1 more than the denominator's degree, we're going to do polynomial long division to find our oblique asymptote. Now when we do polynomial long division, we get a remainder of -5, and we don't worry about the remainder. All we worry about is the quotient, where we got x plus 3 as our answer for polynomial long division. And so our oblique asymptote will be at y is equal to x plus 3. Remember, you're just taking the answer, the quotient from the division, and you're putting it in the equation y equals x plus 3. If my numerator's degree is greater than the denominator's degree by 2 or more, so we did in example 3 was if it's greater by 1, then we follow example 3. But for rule 4, if it's greater than 1. So in this case, we have x to the 5th over x squared. That's greater by 3 degrees. So this applies. We're not going to have any horizontal asymptote, nor are we going to have an oblique asymptote. And so that's easy to know as well. Look at these rules. Number 1 and number 4 are the easiest ones. You either have y equals 0 or you have none. Number 2 is the next easiest. It is very easy just to grab the leading coefficients. And then number 3 is the most involved. We actually have to do some polynomial long division to get your oblique asymptote. So question number 2 asks us to find the vertical, horizontal, and oblique asymptotes, if any, of each rational function. The first thing we have to do is factor. Now when I factor, I notice that there's a factor in the numerator and denominator that match. I'm going to reduce my rational function and come up with a reduced rational function. Now, the question's not asking us this, but if we were to ask the domain, we would do the domain off the original function. So my domain would be all real numbers except -5/2 and -1. However, if I'm looking just for the vertical asymptote, I'm going to only look at the one that did not get reduced. And I get that vertical asymptote from the 2x plus 5 in the denominator. I always write my vertical asymptotes as x equals, and the value is -5/2. So there's my one vertical asymptote. To find my horizontal and oblique asymptotes, I want to look at the degrees of the function, and the degree is x squared over x squared, so it's degree 2 on both the numerator and denominator. That is option 2 when I'm looking at the rules for asymptotes. And so all I need to do is take a look at the leading coefficients. I have an invisible leading coefficient of 1 over 2. And so that's going to be my horizontal asymptote. And I always write my horizontal asymptotes as y equals. And there we've done question number 2. For this next question, we have p of x is 4x squared over x cubed minus 1. Let's go ahead and factor the denominator. Now this is a special difference of cubes, so that's a formula that you should already have memorized. And we have x minus 1 as our linear factor, and x squared plus x plus 1 as an irreducible prime factor. And so looking at this, only one of these could be set to 0 and solved and have a real value. In this instance, my domain will be x is not equal to +1, but x can be any other real number. Nothing cancels out with the numerator, so that value where x is not equal to 1 is also going to be my vertical asymptote. But notice the difference between the way we state our domain and we state the vertical asymptote. The domain is x is not equal to 1, where my vertical asymptote is x is equal to 1. And then to find the horizontal asymptote, we look at the degree of the numerator, which is less than the degree of the denominator. We have x squared over x cubed. So since the degree is less in the numerator, we're going to go with the first rule, which is we have a horizontal asymptote at y equals 0. To do this last problem, we want to factor the numerator and the denominator. And we get these factors. Once again, the numerator has a special formula that we follow for the factoring because it's the sum of cubes. And we notice that none of those match up, so nothing gets reduced. Once again, I like to write my domain even though it's not asked for. My vertical asymptotes are going to be at each hole in the domain. So I'm going to have 2 vertical asymptotes. One at -2 and one at 7. There's both of my vertical asymptotes. Now to look at my horizontal or oblique asymptote, I want to look at the degree of the numerator and the denominator, and I have x to the 3rd over x squared. And that's greater in the numerator and only greater by 1. So we're actually going to have to do polynomial long division. Remember that for polynomial long division, you do have to put in the missing terms. So I'm going to put in x here. X times x squared is x cubed minus 5x squared minus 14x. We're going to switch all the signs by subtracting, and we're going to be left with 5x squared plus 14x plus 1. X squared goes into 5x squared 5 times, and it actually doesn't matter if we do this step because we don't care what the remainder is, but I'm just going to do it to finish my polynomial long division. And I'm left with 39x plus 71. Those first terms canceled out. So this is my quotient when I do polynomial long division. Therefore, my oblique asymptote is at y is equal to x plus 5. And you only either have an oblique asymptote or horizontal asymptote. You can only have at max one of either of them, and you can't have more than one. So we're done. So we found the oblique asymptote, the vertical asymptotes, and as an extra bonus, we also found the domain. Keep on practicing this. This is important stuff. And I'll see you next section.